that x is complex. And remember, real numbers are just complex numbers with zero imaginary parts, right? Now, the nice thing about this problem is we don't have to find, there's 6 of them, 2 real, and then I think 4 complex numbers with non-zero imaginary parts. But this is the typical kind of problem that's popular these days. You're going to evaluate this without actually having to know these 6 zeros or these 6 roots. Now, this very first step here is it's motivated in the sense this is the only given, so we may as well divide our given into the expression we're trying to evaluate and hope for the best. Now, this is the result of the long division. Again, I didn't bore you with those details, but this is the quotient. This is the dividend, right? And then this is the remainder, okay? Now, what we're going to do is we're going to get some mileage really quickly out of this construct. You know, you can rewrite, if you multiply through by the dividend, you get this more common expression, you know, the remainder at the end and the product of the divisor and the quotient right here. But notice that it's sometimes you go, what? It's right there and you don't notice it, but this entire expression is equal to 0. So that means this entire circled part here, this entire circle piece is necessarily going to equal 0, right? That's good news, right? It's very good news, okay? In other words, this part is equal to 0. You multiply 0 times this part, and you get 0. So what we get here, again, problem, this isn't super exciting for me because I designed the problem, you know, and you can just design these things to work out. But notice that this part goes away, and so you have 63x up here plus 108. 108. Okay. Again, y'all, that's because of this given. This given is identically equal to 0 for all x. You can think of that way as an identity as far as this kind of formal processing here. All right, and so that's where this, if this part's equal to 0, this whole product is equal to 0, okay? So that means the numerator right here is just simply this object that we're talking about. Now, what about x to the 6? That's a little strange. You know, what do we do about x to the 6? Well, again, we get some mileage out of this initial condition. If you add 7x plus 12 to both sides, you get x to the 6th. And this is the kind of the miracle, whatever you want to call it, that makes it work out relatively nicely. 7x plus 12. But again, every math problem that seems hard is just a relatively easy problem worked in reverse. Okay. Now, so since we know that x to the 6 is equal to 7x plus 12, we can substitute it right down here. So we're going to write down 7x plus 12 directly underneath this in the denominator of the quotient. And you guys can sniff this out pretty quickly, right? Designed to work, right? So 9 is a factor of 63 and 9 is a factor of 108. So let's keep writing on the next line. So this would be equal to 9 times the quantity 7x plus 12. Plus 12. And again, by design. And that's how a lot of these math competitions work, I think. You know, they look really, really hard, but somebody has just worked the thing in reverse where they know the answer and then they're making you come the other way. It's really kind of sinister in some sense. All right, so these two factors, provided 7x plus 12 is not equal to 0, cancel, and we get a solution. That entire, get a little more space here. This is going to be equal to 9. Right, now we do have to, a little bit of caution here. That's provided that 7x plus 12 does not equal to 0. And this is something that's neglected in textbooks by teachers and kids alike. You know, it's real easy to forget this. It's not a super big deal because you can say this expression is equal to 9 almost everywhere and be precise what you mean by that. You know, but anyway, this would be x cannot equal to minus 12 over 7. As long as x is not equal to minus 12 over 7, our original expression is identically equal to 9. So that's the answer right there, ladies and gentlemen. And I hope you enjoyed that one.